Hello guys, in this video we'll continue to explore the geometrical interpretation of complex numbers and how we can use geometry in complex numbers to solve questions. So let's get started. Here is a question that is being given to us, that mod z1 minus z2 equals to mod z1 plus mod z2. Then we have to prove that z1 z2 bar equals to z1 bar z2. Okay, so we can prove it. So but first we have to analyze it, that what geometrical meaning it argues. Okay, so let's solve it. Let's call it z1 as point A and z2 as point B. Okay, we can call it very easily, so just for sake of naming it. Then mod z1 is actually position vector, so it is OA defined from origin, and so this is very basic definition. Now according to the question, z1 minus z2 equals to mod z1 plus mod z2. Okay, this is AB, this is distance between 2 points A and B, that's how we define in vectors, and this is mod z1, so this is OA, distance from origin. As we know that we can replicate the notion of vectors in complex number for geometrical interpretations. So mod z1 is actually position vector at A and mod z2 is position vector at B defined from origin. Now we can plot this geometrically. So these points or A, B and origin are actually collinears, so we can actually plot, and we can see that OA plus OB equals to AB, which means that A and B are extreme points and O lies somewhere in between them. Okay, so only then it can be equated. So OB plus OA equals to AB. Okay, so it means that origin lies somewhere in between them and all 3 points are collinear. Now let's plot in complex plane. So this is a point A, let's call z1, then this has to be point B, z2. Okay, this is theta, this is theta also, again because origin is collinear with the rest of the 2 points, so we can see this is origin, this is theta, this is theta. So argument of z1 equals to theta, argument of z2 equals to minus pi plus theta. We went minus pi and plus theta. Okay, now what we can do is we can subtract these two arguments. Let's see what we get. So argument of z1 minus argument of z2 equals to pi. Okay, which means that if argument is pi, then we are completely somewhere in real axis, and we know that argument follows the properties of log, so we can write argument of z1 by z2 equals to pi, which means this implies that if argument is pi, we are completely in this real axis, because this is 0, this is pi by 2, this is pi, this is 3 pi by 2, or in Argand plane it is minus pi by 2. So z1 by z2 is purely real. Okay, from this fact we can conclude that if z1 by z2 is purely real, then z1 by z2 equals to z1 by z2 conjugate. Okay, from this fact we can write that z1 z2 bar equals to z1 bar z2. Thus we proved it, and we can actually testify that how easy it is to use geometrical interpretation to solve such kind of complex number problems. And this is all. Thank you. We'll see some more questions on this topic. So here is another question, that it says mod z1 minus z2 equals to mod z1 minus mod z2. Then we have to prove the earlier thing that we proved, that is z1 z2 bar equals to z1 bar z2. One thing that we can really see from the very question is that the right hand side is actually the conjugate of left hand side. Okay, so this is enough to give us a hint that what approach should we use, but we'll solve this with the help of geometry. Okay, let's get started. So solution is Now again, we'll begin from the very basic by the naming the complex numbers as treating them their vectors. So A is Z1 and B is Z2. Okay. Then using the equation we can actually see that it says Z1 minus Z2 is mod Z1 minus mod Z2. This is again AB, and this is OA, and this is OB. Okay, we know that modulus of a complex number is actually a position vector from origin. Actually, position vectors are defined only from origin. So this is the thing, and we can again plot it here. So OA minus OB is AB. What does it mean? It means that B is somewhere in between A and O. Let's say O and A. Okay. Only then OA minus OB equals to AB. Okay. And we can to make it more simple, we can actually write it like this: OB plus BA equals to OA. Okay. Now here we can see that B is in the middle, O is somewhere here, and A is somewhere here. Okay, because we can see this. So OB plus BA equals to OA. Okay. Now if we plot this in Argand plane, what we see is that origin is somewhere here. This is A, Z1, and this is B, Z2. So this is mod Z2, and this whole thing is mod Z1, and this small thing is mod Z1 minus Z2. Okay. Now again, it is very simple. From geometry we can say that argument of Z1 and Z2 is same, so we can write that argument of Z1 is theta, argument of Z2 is again theta. This implies that difference of argument is 0 because points are collinear and they are in the first quadrant, first complex quadrant. Therefore some of their argument will be 0, and we can write this equation again using the property of argument. We can write that argument of Z1 upon Z2 is 0, and if we treat this as a new complex number, argument of a complex number is 0, then we are completely in real axis, which means that again this means that Z1 by Z2 is purely real, and again using this we can prove that Z1 by Z2 equals to Z1 upon Z2 conjugate, and we'll simply cross multiply and we'll get our required answer. So we again proved it, and we can again verify that how simple it is using geometry to prove such questions. Okay. Now remember these. So this is one more illustration in the same row, and we are given that mod Z1 plus I Z2 equals to mod Z1 plus mod Z2. Then we have to prove that Z1 upon Z2 is purely imaginary. So again, let's solve it, and we'll solve it using the ideas of geometric interpretation which we have learned. Okay, so let's get started. Solution. Now again we can treat this as A and we can treat this as B, but to write it more general, in the general form as addition of vectors, we can write it Z1 minus Z1 minus I Z2. It's the same thing. Okay, and we can say this as B and we can say this as A. Let's not call them A and B. So now this is okay, and for a brief amount of time I am calling it as Z0. Okay, so this is actually Z1 minus Z0 equals to, and if we see that this is equals to mod z1 plus mod I z2, this we can expand as mod I into mod z2, okay, and this is actually equals to mod z2. So instead of writing I z2, we can simply write mod z2, okay. So this is mod z2, and instead of that we can also write mod z0, okay. So this is the thing. Now again, this is AB, this is OA, and we can call this as OB, okay. We can see that OA plus OB equals to AB, which means that again O should be somewhere in the origin, in between A and B, and this is A and this is B, okay. If we plot this in complex plane, we'll see that A is somewhere here, okay, A, this is B, this is Z0, and this is Z1, and this is our origin, okay. So we can see that if this is theta, this is also theta, so argument of Z1 is theta, and argument of Z0 is minus pi plus theta. Again, we will subtract these two arguments, and we can write the argument of Z1 minus argument of Z0 equals to pi. Now actually it was argument of Z0 was actually I Z2, okay, this was the thing, and Z0 was actually minus I Z2, okay. So we can do this, okay. So we can further solve it too, using the very simple and omniscient properties of argument. This is argument of Z1, and this is actually equals to, and we'll send this to right hand side, this is equals to pi, this is equals to pi plus pi, and this argument I is pi by 2, so this is pi minus pi by 2, and this minus minus tends to plus here, this is argument of Z2, okay. So argument of Z1 minus argument of Z2 is pi by 2, okay, and using the properties of argument, we can write that Z1 upon Z2 argument equals to pi by 2. If you treat this as a new complex number, then argument of a new complex number is pi by 2. Thus we can write that Z1 upon Z2 is purely imaginary, and that's what we ought to prove. So, and we proved it, and we can now substantially elaborate the importance of geometrical interpretations and geometry concepts that are embedded in complex numbers while solving problems, and this is very helpful for us. So that's all for today. Like, share and subscribe. Thank you.